potentially the idea is to find some material that can be applied at some point, right? So that's the whole idea of this. And you know, the theme again is the designing of materials and designing and discovering new properties with the idea I shared with you. Now, you know, you have been in the quantum materials school. You have been hearing a lot about, you know, synthesizing the materials and so on. So the basic thing in designing the materials or synthesizing the materials, of course, is the chemistry, right? First thing is you need to have a good knowledge about, you know, what elements or what constituents and the material play important role, and what kind of properties, you know, we can think of by, you know, for example, putting one element versus the other element. It can be size, can be electron count, it can be the reactivity, and so on, right? And the other thing, just besides chemistry, sometimes in material science or condensed matter physics, what may play a role is if you can confine or deconfine the charges or the spins in certain way. So the nature of the structure of the materials or the bonding between different planes or the layers can also play an important role. For example, this is a structure of transition metal dichalcozonide material, and the interesting aspect of these transition metal dichalcozonides is that they can be exfoliated and you can create a perfect monolayer. By doing that, you can confine the charges in a two-dimension, right? Much like what was done in graphene. When a monolayer of graphene was exfoliated, right? And then you know, that had led to development of a whole new field of this excitonic physics in these 2D van der Waals materials. That's one of the, you know, way we can think about, you know, when we you know, think about the designing the materials. Another aspect can be, okay, look into how the particular atoms are arranged within certain layer, and the example is, this is just an example, it can be some other arrangement also. This is what I'll be talking about. So here, these black atoms, you see, they make these triangular arrangement, and these triangles, equilateral triangles, are arranged in a current sharing fashion, and this kind of structure is called a Kagome structure. When the atoms are arranged in this structure, then you know, the way that electron can move around or interact with one another can lead to interesting electronic properties, can also generate interesting magnetic properties. I'll discuss about that in a bit. That can be one idea, or you can have, just like in graphene, you can have a honeycomb lattice, and it can give some other interesting properties. So the particular arrangement of atoms also play important role in designing the properties of materials. The next thing is, you know, we mostly are interested in crystalline materials, and in crystalline materials, we have the structure of the material, right? There are various structural elements, the symmetries of the material, and that symmetry also can dictate the properties of materials in a large part. I'll give you one example of that. This is one compound called iron. This is one compound called iron germanium. And iron germanium, you know, depending on how you synthesize it, you can crystallize it in a cubic structure or a hexagonal structure. Structurally, they are different. More than that, what is different here is, if you look into here, this compound has a center of symmetry in it. So if you take a point here, you can find all the corresponding elements in this another layer. But if you look into this structure, this doesn't have, for example, this brown atom doesn't have a corresponding brown atom there, right? So it breaks the inversion center. When it breaks the inversion center, it can generate some sort of new interactions inside the material, which you know, is now famously known as Zelazensky-Moria interaction. And then Zelazensky-Moria interaction can have some effect on the magnetic structure. So that is probably another way of thinking about when designing the materials. So you know, there can be many different ways. These are you know, just a few examples. chemistry, structure, the atomic arrangement, symmetries, and so on. By doing all these things, why we want to do this thing is, we want to find something interesting. So in this, talk, I will, focus mostly on influencing the magnetic structure, and with that influence in the magnetic structure by all these in a synthesis process, influencing its electronic properties. That will be the theme of this talk. So this is just a cartoon that is just made, where we have a ordered magnetic structure, and then by changing, if we change this ordered magnetic structure by some way, with the synthesis route, or by applying some external parameters, for example, magnetic field and so on, then you influence its electronic structure and see how it changes the measurable properties of the materials. So then what we need is, we need the methods, right? How do we do it? Is you get into the lab, and you have been doing all this week. It's a very cool thing to see, crystals coming out of the furnace. When I first made my crystals, I was so happy to see, I remember still my graduate school days, first time entered into the lab, set up a flux, it was a flux growth, and then in a week, open a tube, it's a beautiful crystal, right? So see, it looks nice to see these beautiful crystals in the lab. And then, but this is just the first step, right? You can, think about all these designing principles and make these materials. And then, just making is not enough. Then we have to characterize them well, then study their properties. So, synthesis and study and explore the new properties. We are exploring for new and useful properties in the materials. Okay. From that, now I will get into the topic. The title of this talk is on Kagome lattice magnet. First of all, I just mentioned in a previous slide that when these atoms are arranged in this corner sharing triangular fashion, perfectly making a nice hexagon at the center, we call this as a Kagome lattice. And why this Kagome lattice is interesting is, this Kagome lattice was been studied, more than 75 years probably now. And even in 1950s, people were already studying the Kagome lattice. Because what happens in Kagome lattice is it has this triangular arrangement of the atoms. And if you want to, do antiferromagnetic ordering in this triangular lattice, it becomes very interesting. Because of these, equal bonds. This spin wants to talk to this spin. And how about this spin? This spin wants to talk to this spin and this spin equally, right? So you can kind of either go down or up. And then that gives a lot of degenerate states because of this kind of frustration. So it is, as with every triangular lattice, this is one of the highly frustrated systems. So that has been studied for a long time in this Kagome system. But it is not only that, Kagome lattice, it can generate very interesting electronic properties also. So if you look into the band structures of a metallic Kagome lattice, then in a generic form, very generic form, in a two-dimensional system, a tight binding model gives this kind of band structure. This band structure has very, very interesting properties. One is it has highly dispersive bands here, forming a point, cross point. That cross point is called Dirac point because these the equations of these Hamiltonian is similar to the Dirac's Hamiltonian. And then we have flat band where the electrons don't want to disperse. They come together, very highly dispersive, as well as non-dispersive bands. And as well as this Van Hope singularity inflection point can also give rise to high points in the density of states. And if you can kind of imbalance that high density of state point, you can generate ferromagnetism or even superconductivity. So this electronic structure is very interesting from various different point of views. So this Kagome system is very rich, and one of the current interest, in the recent studies of in the condensed matter physics is particularly looking at into one of the Dirac points. People look at the flat bands also, but the Dirac points. And the reason is that in 2016 there was a Nobel Prize awarded to Duncan Heldon and co-workers about this work that they did in 1988. So basically what they did in 1988 is that they took a graphene. Graphene was not even discovered that time, was all theoretical work. And what this is the calculated band structure of a graphene. And see, you have these Dirac points here at two different places in the brilliant zone. And then what he did is he went one step further, and even in his Nobel lecture, he writes that he did some scientific fiction there, and he put ferromagnetism into graphene at the time when graphene was not even realized. Then when he does that, he did it in two different ways. He broke the inversion symmetry of the crystal lattice itself, and it opens a gap at these points. That gap opening is very trivial, so it makes it just an insulator. But if this gap is broken by inducing magnetism, or meaning that if the time reversal symmetry is also broken at the same time, then what happens is that there appears this edge states connecting one of these bands to another. So these edge states, then he was able to calculate that can quantize the Hall effect in zero magnetic field. So it's quantized anomalous Hall effect. And this has been now realized in topological insulators, right? So there is a great deal of interest on these kind of materials, and since this Kagome system has this kind of electronic structure, and what these Kagome magnets, how do they behave when there is magnetism into the system and when there is intrinsic band structure. But this is all in 2D limit, right? When you start studying the bulk materials, we are in the 3D limit, and then how it plays out, it's a different story, but that is an interesting topic to follow. And that's what people were doing for the most part, right? There are so many kind of this now high profile papers here. You can see this magnetized 3 tin has a Kagome lattice here. Yes?
The previous slide, middle band structure, where's the Fermi level?
So this, the Fermi level can be at a different place. This is just a generic band structure. Okay, depending on your chemical potential can be at different places. You can tune that chemical potential.
Yeah, so that would be a parameter that would tune to
yes.
property of these systems.
Correct. And then I'll get to that briefly. Then in this one you have this is basically it forms this non-collinear magnet because of the Kagome geometry, and that gives rise to this large anomalous Hall effect. And they found interesting Weil nodes in this material also. That's a different story. And iron 3 tin 2, see, because of this, now your chemical potential can be at different places, right? And you can tune that. There is this, because it's a bilayer Kagome system, you have these double Dirac points here, and there was a large anomalous Hall effect observed in this material, and this paper actually tries to associate that large anomalous Hall effect with this kind of electronic band structure in this material. In cobalt 3 tin 2, this particular paper discusses about the flat band and opening a gap at this place, and again giving rise to being able to observe in magnetic and transport properties. And this is iron tin in this material. It was first realized that, okay, in a Kagome system with the photo emission experiment, RPS experiments, they were able to see these the existence of these flat bands and these Dirac crossings in the same material. So that was a general interest. But what I said is that, as a synthesis person, right, yeah, these are all great works. But what we want to do is we want to tune the properties of these materials. How do we tune the properties? What is our tool to do that? Is you want to play with this chemistry, right? You want to change the structure. You want to replace these elements so that you can sequentially change the properties of the materials. For that reason, these materials are not that great because if you want to change the elements, they will either form in a different structure or lose these properties. So I call this a rigid systems, right? So we need something very flexible system if we want to do that. And one of the systems when I was getting into this area 5-6 years ago, was thinking like, oh, can we have some material system that had some of these Kagome features, as well as it's very flexible, so that you can replace one element, the structure doesn't change. If you replace many elements into the system, you can change the electron count, you can change the size of these, you can stretch or contract the material and keep the structure principally the same. So you have these features there. And I came up with this material system that was known for a long time, wasn't studied for this particular behavior. It was around 2018 that we started working on this system. So this is called RMN6 SN6 system. So R is a rare earth element, and Mn is the manganese. Manganese is the one that is these black atoms are the manganese atoms. The green atoms are the R atoms. And the other 3 different colors are tin atom because they sit in 3 different inequivalent crystallographic sites. So they are principally different tin atoms. And then these black atoms, actually these manganese atoms, forms this Kagome in it. So it has a Kagome feature in it. What interesting behavior I found that time is that, okay, this is great, because if I replace any of these rare earth that rare earth by any of these atoms labeled here in green, you get the same structure. So you have this liberty of kind of changing different elements and potentially tuning the properties there, right? Another one is, it was more than that. You can replace this manganese with any of these 3D transmetal elements also. So there is another degree of freedom to tune the electronic as well as the magnetic properties in the system. And it's not only that. Since there are three inequivalent tins, it also allows you to maybe selectively replace one tin from one side, right? And that also provides another profound degree of freedom. So you can replace that with gallium, germanium, indium, or tin. With germanium, you can basically replace in all 3 sides. But with others, so far, it goes in. They try to go into only one side. That we learned when we are working on that, and I'll show you in this talk that how we have used this platform to tune the magnetic structure, and then see that effect changing the electronic structure, mainly the Fermi surface. Okay.
Can I ask a quick question?
Sure.
Is there a bismuth version?
I have not seen the bismuth version yet.
Excuse me.
Yes.
So what's the contrast to previous Kagome system were rigid, and what was different in this system? Is it that in the previous system, or in contrast to the previous examples, this system allows more chemical?
Yes. That was my thinking, right? I'll show you, whether I was perfectly right on that one, or we get something different. Okay, now the first system that I looked at into was, I wanted to look into a, simpler system, but turned out to be more complex. There is a reason. Simpler is you have yttrium is non-magnetic. So when you have, R, magnetic R atom, and as well as the magnetic transition metal element, you have 2 magnetic elements competing with each other, right? So that may be more complex. So let us just focus on the one where the magnetism comes only from the transition metal element, which is manganese in this case. And then, see, this material was synthesized. We are not the first one to synthesize several years ago. And these magnetic properties was also known. What was not done is that the phase diagram was not mapped out. So we mapped out the phase diagram, and we found very interesting stuff. right? It orders at about 350 Kelvin, and when it orders in a simple antiferromagnetic state. And then as you lower the temperature, what happens is that, okay, then it kind of the antiferromagnetism distorts, starts rotating from one plane to another. Okay, so to give you the context, what happens is that in each of these manganese layers, the spins are parallel. So they are ferromagnetic in the plane, all pointing in the same direction. So when it goes to the next plane, it also is parallel, but in the third plane, it's kind of anti-parallel. And double layers moving together, right? One pointing in one direction, the two layers pointing in the opposite direction. That's how you get the antiferromagnetism in this case. And then you apply magnetic field, in the plane. Then you generate a lot of different magnetic phases. This is DS is distorted spiral. This is transverse conical spiral. This is fan-like phase. Some incommensurate phase, and then it becomes ferromagnet finally. So what we did in this work is we then in order to know the structure, how these structures are arranged in the material. Neutron has the moment, right? That spins of this neutron can interact with the ordered spin, and in a very much similar fashion as we use X-ray to know the structure of crystalline structure, we can know the ordered structure of magnetism in materials by using the neutron. And we collaborated here at NIST with Jeff Lynn and his group. And then we determined the magnetic structure, and we needed some help from theory also. Sometimes theory is also very helpful, especially in we were having difficulty in identifying this phase, fan-like phase, and my colleague at George Mason, Igor Mazin, he came up with this structure by pure calculation, and then it matched perfectly with the experiments. I will not go into that detail because this talk is not for that. Here, just I wanted to show you that, okay, there is this distorted spiral, the spiral stage distorts a little bit, and then spin does something very amazing. It wants to go out of plane when you are applying magnetic field in this direction, right? And then it flops back into the plane and form this phase and goes on. So there are many different magnetic structures that we can determine. Why we are even interested in determining this magnetic structure is that during this process, what we found is that in one of the regions, on one of these phases, we saw very unusual behavior. That means when we were measuring Hall effect, it had some additional signal that was not supposed to be there, which, again, I will not go into the details of all these things. If you measure the Hall effect, then you get from the electron count. Every conductor has this part, this normal anomalous Hall. Then if it has magnetism, especially ferromagnetism, or now these days even antiferromagnetism, you can get the anomalous term, which comes from the band structure part. But there was some additional signal, and this was some other group also reported during the same time, and they did a little better job because they mapped out the whole phase by doing very, very detailed calculation. That it was appearing only at a certain range of temperature, and especially the interesting thing was at high temperature. Whereas the magnetic structure was same from 1.8 Kelvin all the way to 300 Kelvin. So that was something that puzzled us, and therefore identifying the magnetic structure was very important to know why this is happening. Even when we determined the magnetic structure, that magnetic structure itself was not supposed to give this behavior. So there was some theory involved, and what we realized that, okay, actually temperature is helping it. Temperature, what temperature does is that it fluctuates the spins, and that particular structure, when fluctuate with temperature, can generate some features, what we call a scalar spin chirality, that can generate this kind of Hall effect. So that was one way. See here, there is some structural part also. Because this Ghimire lattice is very two-dimensional, what happens is that when you put a spin in a completely two-dimensional system, there is a theorem called Mermin-Wagner theorem, and what it says is that you cannot have an ordering of spins in a perfectly two-dimensional system, which now is not entirely true in some material cases, because recently in completely two-dimensional system, people have found ferromagnetism because of the anisotropy and so on. but that theorem still holds, meaning that it generates a lot of fluctuations. So this is a manganese system, and the manganese is fluctuating highly, and that fluctuations is enhanced by the temperature. So at high temperature, you can get this scalar spin chirality. So the structural part was also important, not just the Kagome part here, being the two-dimensional was important in this case to get this state. So with this, then we observed one another very interesting property. It may not be interesting if you look at into only this compound, but I will try to make it, when we start tuning these properties, how this evolved makes it interesting. That just remember that there are two. This is I'm measuring here. What we are measuring is electrical resistivity, simple, and we are in the red one we are passing current along this direction. In the blue one we are passing current along this direction. So the spins are ordered like this, right? There are ferromagnetic spins here. They rotate slightly along this direction. So after 8 unit cell, it repeats along the c-axis. That gives you the spiral state. And as kind of you can expect that it will be easier for electrons to move parallel to these spins in the plane, the resistance is less in this case. And when spins, when these electrons try to move along across this line, the resistance is higher here. It's perfectly normal, nothing unusual there. Okay, just looking at into this. But now, as I told you, that our goal was to tune these various different properties. And how do you tune it? Is that we took the same material, and we had to be simple, not very complicated. So I told you that there were 3 inequivalent tins, right? And the advantage of that is that you can replace one of the tin and then put back another element. So the nice thing is, let's keep the electron count the same. So let's look at into the periodic table, and tin is here. So if I put germanium, so the germanium has the same electron count. It necessarily will not change the electronic structure. But what it does is that it has a smaller size. So it can shrink the crystal structure, right? When it shrinks the crystal structure, what changes it can bring in the magnetic structure, or even in the electronic structure, because of the magnetism. That's what we wanted to study. So we replaced the tins from this side. This side is called 2C side, and with the X-ray, it's very kind of reliably, you can know that it has only replaced tin from that side. And we replaced here. But there is one thing that I have still not discussed with you, is that in this material, the most important or interesting aspect is the interaction of these spins from layer to layer. Within one layer, these manganese atoms are strongly interacting with one another, so they are a ferromagnet. But these manganese moment here, they can talk to the manganese moment here, and this interaction is labeled as J1. This is exchange interaction. Then, likewise, this manganese layer can also talk to this layer, and this is not same as this because of its structure. The beauty of this structure lies here, because you see here, between these 2 layers, you have only tin atoms. These 2 different colors are tin atoms, right? Although they are sitting in different crystal website. But between this and this layer, if you look at here, you have this rare earth element, Y, which is yttrium in this case, as well as tin atom. So the interaction through this layer and the interaction through this layer can be different. Okay? And then you can add the next nearest neighbor interaction, which is this J3, that can be important in some instances. So when I told you the phase diagram, I said that it orders into first antiferromagnetic phase. At high temperature, J3 is energy, right? So that doesn't kick in. And when you lower the temperature, that J3 becomes important. And then that J3 tweaks these, helps in turning the spins in this material. That way you get a spiral state. Okay. Now when I replace germanium here and squeeze it, I'm influencing J2. At the same time, I'll be influencing J1 also. And all your magnetism is coming because of this J1, J2, J3. Right? So let's see how that has affected the properties. We looked into the magnetic susceptibility between the parent compound and then the one with the germanium. It wasn't, very different when we look just at the susceptibility, right? They look very similar. The transient temperature barely moves. It was 345 Kelvin, 343 Kelvin, but when we look into the transport properties, we could see a stark contrast between these two. So these dotted lines are for the parent compound, okay? This one is for C-axis resistivity. The blue one dotted line is the in-plane resistivity. You see the same in the germanium compound. Then, this is a doped compound. Usually when you dope, you are messing up with the structure, and then your resistance, you expect to increase. Here the resistance is becomes smaller, because this is a complete replacement, right? So you are replacing whole tin with germanium. So it's still a line compound. And it's telling us probably something about its electronic structure looking at it here, because what happens now, see the switching of this thing? The red one is on top of the blue one here, and that switches here. So somehow when you put germanium into it, the electrons find easier to move perpendicular to the layer, unusually, right? Then moving in this direction. So that is, one clue for us to see that, okay, it might have changed something electronically, although this is the isostructural dope, right? And then this is basically just the ratio of the C-axis conductivity over AB plane conductivity, and this is smaller in the parent compound and large in the doped compound. So C-axis conductivity is enhanced, basically, the theme is. Now, let's look at the magnetic structure. Now next, we had already studied the first parent compound. We wanted to study the doped compound also and see how it has influenced the magnetic structure. So the similar study showed us, let's pay attention only to this, that these were the angles of turn, because it has a spiral state, right? So it's turning from one layer to another layer. Basically, it changed slightly the turning angles. Here the turning angle was determined to be negative between these two and was slightly larger. Here slightly smaller but positive. That is all. And that change in angle was good enough to change its electronic properties. And how did we know that this was changing the electronic properties? That we could calculate, because we measured something interesting in the resistivity. And the resistivity comes from the effect that is happening at the Fermi surface. And we can calculate actually something called plasma frequency. In plasma frequency, it comes just from the Notre model, that the plasma frequency tells you about the anisotropy or isotropy of the Fermi surface, okay? And when we calculate this plasma frequency along Z and in the AB plane, we found is that there was difference between the parent compound and the doped compound. So from this calculation of the plasma frequency, we could see that it had changed the anisotropy of the Fermi surface. And this was very consistent with what we got here. This basically, you can relate this plasma frequency to the conductivity of the material, and you can calculate this plasma frequency along C-axis and in the AB plane, and you take a ratio, and these are the plots for the ratio. The blue one is for the germanium compound, and this is for the parent compound. We get a similar state here. These calculations were done in 0 temperature, right? So at low temperature, you can see the same behavior. So basically, by putting germanium, you change a small, you brought a small change in the magnetic structure. That magnetic structure led to a change in Fermi surface that you can measure with, basic resistivity measurement. That was one of the stories. And now, what happened with these interactions is that I told you that the germanium will shrink basically that second layer, and it can influence J2. these are the calculated values for these G's for the parent compound, and you can see that this is negative, meaning that is a ferromagnetic interaction. Here, this is antiferromagnetic interaction, and then there's the J3 is ferromagnetic here, right? But when you put germanium, it reverses this because it brought change here, and it makes it ferromagnet also. But this is very small, as you see. The ratio, this is experimentally determined ratio. From the angle, you can calculate these ratios of the J. Just calculating the J is difficult this way. And once you calculate that, then you see that this sign of this one is reversed, and this one is also reversed. And because of that, we see these changes. It's all about playing with the exchange interactions that drive the magnetism in the system. Now, what after that, right? So then I told you that even putting these gallium, you can put gallium or indium in place of the tin. That's what we try to do next. Let's put little gallium. Now, let's just not make just the isostructure. Let's change the electron count also and see what it does. Then we try to grow this with the gallium doping, but with the gallium doping, it's very hard. Again, this is a chemistry, probably chemistry related question. That it doesn't want to go, gallium doesn't want to go too much into the system. We could put at maximum maybe about 0.55 or maybe slightly more. The compound that we studied had this composition of gallium 0.55. It was replacing again tin on the same site because calculations suggest that there is a huge preference for this replacement at the 2C site, this site over any other site. And when we put this gallium, you see the magnetism is completely changed now, right? It was antiferromagnet-like behavior or spiral states. Now, just by looking this, you can say that, okay, this has become a ferromagnet with just a very small amount of gallium. And, why would you care about making something a ferromagnet? This was very important to us. Although the ferromagnetic property itself is not interesting, there was some, properties associated with the anomalous Hall effect was made that, okay, it is because of the churn gap or anything in one of the compounds that has this ferromagnetic interactions in one of these 1,6,6 compounds. And when we were studying, we were not getting that. So this compound actually making ferromagnet allowed us to test that. I'm not going to talk about that, but it was important. At least it was very important for us to get a ferromagnetism in this compound. And why does it gets into the ferromagnetic state? Is again because of the way that the gallium changes the interaction between these elements. And what they did is we took help of some calculations for this. Is that now see here in the parent compound. This was negative, this was positive, the value was about 5 here. Now this becomes significantly larger than negative in this case. And now what this means is that this is a ferromagnetic interaction, this is also a ferromagnetic interaction, they are comparable. So they are hard to kind of twist by the third interaction. So they prefer to be, parallel with one another in every plane. And then we get a nice ferromagnet, that's ferromagnetic in the plane. Okay, that was one other, we were changing the spin structures, and that allowed us to study some thing in the electronic structure by changing the crystal, some parameters in the 10 minutes, okay, sure. And I'll brief on this one. This is another compound. Here, now this is terbium. Now we replaced yttrium with terbium. And then what we get here is that now we have this J1, J2, J3, all the magnetic interactions. On top of that, we have now terbium also is a magnetic element. Now there is interaction between terbium and manganese layers also, right? So there is another J here. So the J effective becomes different here. And in this case, because of this additional interaction, these elements wants to be parallel all. These manganese wants to be ferromagnet in each layer. Terbium wants to be ferromagnetic in each layer, but they are pointing in opposite direction. That kind of structure is called ferrimagnetic structure. And what was very interesting about this compound, is that this orders at about 420 with this kind of in-plane ferromagnetic order. As you lower the temperature, what happens is that now these ferromagnet lying in here, they want to go out of plane. They still are like that. They were like this, right? And then when they move to the out of plane, they do simultaneously like this. And you can see that by measuring susceptibility, right? In one direction, susceptibility was small here, and then it goes, right? So the spins are pointing along this direction, which is the c-axis. And here, originally, the susceptibility was large because the moments were in the plane. And then when these spins go out of plane, the susceptibility drops. And I'll tell you that very interesting feature has been realized in the region where the spin reorientation happened. Actually, I will skip this because we were able to explain what, because of this two-dimensional nature of the magnetic ordering, that enhances the fluctuations. And that fluctuations play a role in doing this for this spin reorientation. But what I will show you is that right here in this region, these bispermionic texture were discovered. This was not our work, it was some other groups' work. But I'll tell you, in one of these R166 systems, we have been able to engineer this fermionic texture that has yet to come. We published, so I didn't put it into this talk, but it's very interesting. Okay, and then now it's not just let's go into some brother or sisters of Kagome. Kagome is, you have perfectly hexagonal system here, right? The corner sharing equilateral triangles is the definition of Kagome. But what happens when it goes slightly deviates from the perfect Kagome net, that these triangles are still equilateral, but there is a twist in this hexagonal pattern. So we named this as twisted Kagome. And we found that there is a large family of R166 compounds that have R is rare earth, sorry, not 166, R111 compounds that has this twisted Kagome geometry. And this twisting can generate some anisotropy within the plane. And you can play with that anisotropy to again play with between some external parameters and the magnetism in the system. And you can maybe generate very interesting properties in the system. I'll show you an example of that. I'll be very quick because of the time. So this is a structure of a material. The R is a rare earth and AGG. There are hundreds of materials in this family again. And then these blue atoms are the rare earth atoms. So here rare earths make the Kagome net, which is interesting in itself, but this makes this twisted Kagome net in the plane. And this particular compound that I will show you some data about is the holmium silver germanium. It orders below about 11 Kelvin, and it has another second transition below 8 Kelvin or so. So there are two transitions. The interesting one is the lower one. So I'll basically focus on the lower one. This is the resistivity, showing similar transitions here. Now, when we measure magnetization, it shows a lot of different steps in the magnetization. And this steps has to do with the twisting in the plane. Okay, because it generates huge anisotropy in the system with holmium atom. The choice of atom also matters. Particularly with the holmium, it generates huge anisotropy in the plane. And then by applying external magnetic field, you can change that, and then you can kind of get these magnetization steps. How we get these magnetization steps is that we are fortunate because this compound was studied for a different reason. They were just studying the huge anisotropy in the system, and was even published in Science on this material. That they proposed this as a perfect spin ice system. We are realizing that it's a spherical chicken model because there are little details that were ignored in this paper, but to most of the part it captures this thing. So this is the spin ordering in this material. So it's very complicated, but for that reason I've kind of put different colors for different spins. So these green atoms are, so this is a hexagonal system, right? In a hexagonal system, the crystal structure becomes a little bit trickier to label because this is A-axis, this is B-axis, but I label this as Y-axis as 1, 2, 0, which is perpendicular to A-axis. That direction is. When magnetic field is applied particularly to that direction, then these spins are labeled with reference to this 1, 2, 0 direction. Any spin that is parallel to 1, 2, 0 is green. Any spin that has some positive component along 1, 2, 0 is red. So you can resolve this in this component here, right? All these spins have positive component on this direction. If a spin has a negative component along that direction, then that's blue. When you apply magnetic field on this direction, first it wants to flip these that are parallel to the spin because the magnetic field talks to them easier, right? It flips this one spin and you get one step. You increase the magnetic field, it flips another spin, you get another step, right? Then it starts flipping, it doesn't touch this red because the red has already the positive component along the direction of the magnetic field. Then it starts flipping the blue atoms. When it flips blue atom, then it gives the third step. So there are these 3 steps. That's how this description in this science paper is given. Okay, but that has amazing transport properties. So this is again, these are this different state. I call this UUD state because 2 up, 1 down. Then you apply another field. You make all these spins parallel UUU, and then still here the blue atoms are not touched. Then you apply further magnetic field. The blue atoms also become the red atom because they have components now along the B-axis. Then this gets into a different magnetic state. Then it becomes extremely difficult for them to be polarized. We measured it maybe even up to 70 Tesla at Los Alamos, and it doesn't saturate there. It kind of keeps growing. So it's a huge anisotropy. Okay, so what is interesting is that now there are these different steps in the magnetization. We measure the Hall conductivity, and in the Hall conductivity, you see that there are these little steps going up here. And then when it enters into this region, it boom, comes way down. And this is where people have fallen down. There is one even published in PNAS saying that, okay, this is a large topological Hall because, this was not supposed to come and this is a huge jump. This is not a topological Hall. This is change in electronic structure because the spin structure becomes different. What we realized is that actually for that you need to look into the temperature dependence of this. So above the magnetic ordering temperature, this black curve is all negative. So this is n-type. It shows n-type behavior. The electrons are the majority carriers. Okay. When the antiferromagnetic ordering happens, the magnetic structure becomes large. It's a 3 by 3 or root 3 by root 3. And then because of this large spin structure, the electron band folding happens. Because of the band folding, you have hole pockets more than the electron pockets in the Fermi surface. So that makes your conductivity positive here. It's negative, right? So this is a hole-like behavior. Okay, and then these jumps, 1, 2, 3 jumps, doesn't change the magnetic structure. It flips the spin, but its magnetic unit cell remains the same. And then when you flip the blue atoms that were in the chain, then it goes into 1 by 1 structure, meaning that its unit cell, magnetic unit cell, becomes similar to the structural unit cell. So your bands will become similar to that in the non-magnetic state. And you are recovering that electron pocket. That's how you're getting this kind of huge drop here. And you see between 4 Kelvin and 1 point Kelvin, there is a significant change. I don't have a proof, but what I think is that this may be related to formation of, because of this coming from the drag points in the system. The reason I'm telling you that this is the band structure calculated in the non-magnetic state. It has this drag point here slightly above the Fermi energy in that state. Okay, and then some one-dimensional flat bands also, some reminiscence of the Kagome system that I showed you earlier. Okay, now your system is ordered, and then it becomes, root 3 by root 3, your band is all messed up, right? So it's not as nice as this one. But when you go into that final state of this magnetic structure, then this is the band structure for that particular case. You basically recover these bands. And because now it has a magnetism, the bands split here, and it brings these flat bands and the drag point right at the Fermi energy. Okay? It is not only the change in the Fermi surface topology, but tuning these interesting features right at the Fermi energy. And that may have some effect on the electronic structure. And more than that, what we found, this is only some hand-waving argument. Some amazing thing happened in this material. Now apply magnetic field along this direction, not along this direction. Okay, that was studied by other groups also. This was not studied by any group, interestingly. We found that there are these similar features. There is a drop, maybe there is a change in the electronic structure here, and then it tries to kind of follow the same behavior as in the other direction. But above this 5 Tesla, it goes again boom up, where there is no change in the magnetization. So this is a puzzle still. We don't understand why this is happening, but this is very unusual feature. And we measured in multiple different samples. If we look at the temperature, I'm only plotting the positive field here. Okay, by the way, there are 2 colors here on the magnetization, right? When we are fighting with the review, one of the referees said that, oh, you can have demagnetizing field. And then that could be the reason why this feature is we are observing here. So what we did is we preserved our Hall sample. We took off the leads from the Hall sample, and we measured the magnetization on the same sample. So by geometry, there is no demagnetizing effect. So that's the pink colored one. There is only a small change. Okay? So this is real, and if you change temperature, you see at 4 Kelvin it becomes more pronounced. It comes towards the lower side temperature. There seems like there is another transition at high temperature, high magnetic field even at 1.8 Kelvin. And then at 5 Kelvin, we still see that, and then it disappears above 6 Kelvin or so. So that low temperature magnetic phase seems to be very interesting. We measured another sample, we put to 14 Tesla. In 14 Tesla, we see this, drop at about, 12 Tesla, where there is no change in electronic structure, and we can recover the same feature at 4 Kelvin as in the previous sample. So this is something very interesting, and could be, very interesting interplay between your magnetic field and the spin textures. So, maybe there are some very, very degenerate states that doesn't change your magnetization, but for the electronic structure, that change is good enough to, bring all these changes. So I'll summarize my talk now. So the idea is to design materials and discover some interesting properties by synthesis method. So we have all these kind of tools with us. We can kind of make our hand dirty and then work in the lab to do all this kind of stuff, and with the particular kind of physics in view. And then, I talked about this MN6, SN6. I showed you that it's a very flexible system, and that system allows to tune both electronic and magnetic properties, right? So it's crafting the spins there. And then, even slight twisting in the structure, you can craft again a spin that way also. And here, external magnetic field was very interesting to drive this system through different magnetic states and then change its electronic properties. All right, with that, I would like to thank you.
Questions, please.
Yes.
So when you have like calculation for J1, J2, and J3, that's from the resistivity equation?
No, that was just from electronic structural calculus, first principle calculus, first principle, not electronic calculus, first principle calculus. Yes.
Over here first.
Yeah. So in your like YMN6 example, you are like able to replace with like germanium and other and you gave had like a specific like stoichiometry, for example, zirconium-2. Were in your like reaction, are you able to change the stoichiometry or like
Yeah, very good question. I think you are getting, the theme of it. Yes, we can do various different compositions of germanium. You can replace whole in germanium also. But, we wanted to stick to 2 for a particular reason, because, we want to compare our experiments with theory, right? Then we can have a better understanding. It is easier if you replace everything. So your calculation is just like a line compound. Right? You don't have to, deal with this doping effect. Yes. So for that reason, we wanted to stick with the composition 2. So it is, meaning that there are 3 inequivalent tin here, right? One is this, this, and this. So you replace all of that, and even if it is a doping study, it is still a line compound.
No problem.
So what about the first half of the lanthanide for 1660? You start with the gadolinium and
So if you go beyond, then it changes the structure a little bit. That's sorry. Here, right? These distort the structure a little bit.
we are not getting this.
Yeah, it doesn't give the same structure. Yes.
And the second question is related to your gallium substitution. So can you please pull up that slide? Like just coincidentally, if I remember correctly, changes from antiferromagnet to ferromagnet. TC or TN is of the same temperature, like
Similar. Yes, you can see the TC remains pretty much the same.
yeah.
Maybe go a little higher.
Do we have like neutron for that?
There is some other group work did Newton diffraction also, but for a ferromagnet, it's a ferromagnet, right? Then what you get is just some peak at Q0 lines, right? So yeah, I think there's some other group from, I think it's from Michigan State. They have done Newton studies on this one. Yeah, our focus on this one, and then to study this one was to make a ferromagnet, and through the ferromagnet to show the 3-dimensional nature of the anomalous Hall behavior. Just saying that, okay, there is nothing to do with any Chern gap type of physics in this material. This can be coming only from, so what happens when you make a ferromagnet is that it splits the electronic bands. And when you have a splitted spin up and spin down, the degeneracy is lifted, right? And then you can have some curvature in those bands, and which we call Berry curvature. So all ferromagnets are supposed to have Berry curvature, and that can give rise to anomalous Hall. You don't need to invoke some exotic physics to explain the anomalous Hall observed in these materials. That was our and that is what we discuss in this paper.
So is there any effort to change the transition middle site such that you can separate layers more?
Yes. This family has been extremely popular these days. And then I see I always forget my friend's name in Washington, Seattle. Junhao, yes. He is replacing the transmetal element, and I'll tell you without telling the name of this, we recently did that, and we have amazing result.
But meaning mix it so you can have distinct layers,
On the transmetal, no, because this is crystallographically same, right? So tin is interesting because it sits in different Y composition. So there, the affinity in going into one layer versus another layer is different. So there so far we have not tried beyond tin and the germanium. Both of them, germanium and gallium, both of them has huge affinity to go into 2C site. Calculation also suggests that.
I'm just saying, if you could separate these layers more somehow.
Yeah. Oh yeah. Yes.
It seems to order very easily.
Yeah. Oh, I see. I got that point. Making it larger instead of yes.
Okay. One more? Yeah. Linda.
that's an excellent question. I mean, I think it has some, there's some inelastic Newton result in FQM2025 at least, done by, again, group in Michigan State. And it's consistent, although it's not, perfect, and there is issue probably in that analysis also, experimental analysis also. But it gives us a guide for germanium. What we did is, when we had this angle, I should have some slides here. At least for the germanium, it's partially experimental also. Let me see. I have this. It's right here. Yeah. We use this, we calculated this alpha, beta, gamma from alpha and beta from the experiment, right? And then we use these equations to actually get the ratio. We cannot get the values particularly, but we can have at least the knowledge about the sign of these things by this ratio. So in germanium sample, it is, yes, it's kind of partially experimental, I would say. But in yttrium, the one that I showed is all calculated stuff. It's not very far from what is reported experimentally. You do inelastic experiment, you can get this information, right? But there also is, you need to model for that.
Okay, so thank you so much, Nirmal.